So hey everybody, thank you Chris for organizing this. It is a real privilege to be able to do this. My name is Jed Sundwall. I work at AWS. Many years ago, I built the open data program at AWS, at which time we launched Landsat on AWS, which is kind of consequential for COGS. I currently work on the sustainability team at AWS, focusing on decarbonizing our business. But like Chris, I'm not really here on behalf of AWS. I'm here as a member of this community. And so I'm going to talk a little bit about just what a COG is for those of you who aren't familiar with the format at all, and give a very brief overview of raster data, and then talk about some of the principles that went into the creation of the COG when we launched Landsat on AWS. And you'll hear a lot of echoes of what Chris and Howard just talked about with regards to moving beyond desktop software and making data available in very discrete, crawlable ways. And then I'll talk a little bit about the COG ecosystem, but I don't want to dwell too much on that, just because I think that's the whole point of the next 2 days is to explore that ecosystem. So first off, a COG is just a GeoTIFF. It is just an image made up of pixels, and each of those pixels represent data about something. In the case of any GeoTIFF, it's about somewhere on the planet. And so what you see here, this is an image that from a NASA website, just showing off the different layers of data that you can get with a Landsat scene, which includes visible light, it includes infrared light, it includes thermal data. And each GeoTIFF is an image that shows you, it gives you data in the form of pixels of how much of these certain wavelengths of the electromagnetic spectrum are bouncing off of the planet at any given place. This is a somewhat more abstract view of what raster data looks like, but that emphasizes the fact that each pixel represents a data point. So there's this much blue reflecting off of this part of the planet, there's this much green, et cetera, et cetera. But one of the cool things about raster data is that you can encode really anything that you want. So, I mean, Chris is giving examples about like mortgage rates and things like that. You could include, information about mortgages in the area encoded in a pixel. You can include elevation data in pixels. You can include population density, really anything. And so raster data is very cool because it provides a very convenient and efficient way to encode data about a place that can be used very flexibly. Now, traditionally, so this is, you're gonna hear some echoes here of the old sort of desktop approach to sharing data. Traditionally, the way that you would get Landsat data specifically, but a lot of GeoTIFF data would be bundled up into archives. In this case, what's called a tar ball or a tar archive. There's a clue as to why this is not optimal in the term tar. To say tar archive is kind of like to say ATM machine, because tar stands for tape archive. What you're getting when you get one of these archives, these bundles of data, is something that's trying to mimic the past experience of putting a bunch of data onto a tape and transferring it that way. This made sense back when we relied on putting data onto physical media to transfer it. It made sense if you had to worry about concurrent downloads and you didn't want to make a lot of requests. It doesn't make sense anymore. And so one of the first things you do with COGS is that you break out the tar archive. So liberate the data from the archive and allow people to get whichever band of data that they want. So if you want the GeoTIFF that corresponds to just the visible red, blue, and green light, you should be able to get those TIFFs without downloading everything all at once. But if you enhance, you can go a bit even further. So what if you had all these GeoTIFFs and you said, you know what, I only want to do some analysis of vegetation, for example. So you need just a few bands, one of which is shortwave infrared, and you say, I actually only want to look at the vegetation analysis in this patch of rainforest, and I know where it is. What a a cog does is it allows you to skip ahead to just that part of the file. You can skip ahead to a certain tile within the file. Typically with GeoTIFFs historically, the way the pixels have been organized in the file has been that if you were to load the file, it would come in pixel by pixel, row by row. So it'd go left to right, top to bottom, just loading up each pixel. What a cloud-optimized GeoTIFF does is actually rearranges the binary data within the file so that the data loads up within tiles. And so rather than going across the entire row, it will create, it'll go across part of the row and then on down to create a tile and so on and so forth. And what this does is it allows you to make what's called a range request, an HTTP range request. So it says, I want to get part of this file, and I only want to get from point A and point B within the binary data because I know that corresponds to the field or the farm or the patch of rainforest or the city that I want to look at. Range requests are foundational to the web and how data works on the web. If you've ever skipped ahead in a video that you've loaded on the web, you've made a range request. Pay attention next time you open up a video in a browser, and you'll notice there's a slight lag when the video is loading up before the progress bar starts. What's happening in that moment is that your browser is saying, oh, there's a video file here, and it's reading a bit of metadata about that file to learn how large the file is and how long the video is. And that's what allows your browser to know what parts of that file correspond to locations on the progress bar. The same exact thing happens with a GeoTIFF, where there's a bit of metadata at the head of the file that says, hey, I'm a GeoTIFF, I correspond to this part of the planet, and I'm made up of tiles that are this large. And once you have that data, then you can do all this really cool stuff that we're going to be talking about in a little bit. So the main characteristics of a cog are that they are GeoTIFFs. This is actually part of the secret here is that they're just backwards compatible. If you've ever used any kind of application that can work with a GeoTIFF, you can use a cog. There's nothing really special about it. But they just do have these additional constraints or attributes that allow them to work in cloud environments. So like I said, tiles, what I did not mention are overviews, which are coarser representations of the data that allow you to zoom out very efficiently. And then that metadata that I described that's at the front of the file, it's called the image file directory, an IFD. And Howard talked about this, which is, it's a bit of metadata, not about the data itself, but about the file to help you navigate the file and understand what's in there. It's kind of like a table of contents. Now, and then, you know, the funny thing here is that like, you can make a cog and not put it on the cloud. That's fine. Like I said, they're just GeoTIFFs. What we're describing here is the spec of the file. But the truth is if you really want to make these things sing, put them in a cloud-based object store. And any sort of cloud-based object store will allow you to do range requests. It will allow massive concurrency in terms of access and speed and adjacency to massive compute power. So or massive compute power or very small ephemeral compute power, which we'll talk about, which allows you to do things very quickly at large scale and efficiently. So this is what a GeoTIFF might look like in an object store. This is Chris's GCP bucket where he has some cogs, and he's got what looks like a 5 meter resolution, so that's 5 meters per pixel TIFF that shows San Francisco. And so this is what this looks like. What you can do is sorry, I'm going to go back. You can get a URL to that specific file and just plug it into a browser. You plug it into the browser, and suddenly it starts loading up in your browser. You can zoom into it. You can pan and scroll around it, and it'll render in real time. And so you can see it coming into focus as this animation goes through here, and loads up tiles as you zoom in, which is super cool. This is another example of a browser-based cog viewer. You'll see here this is a false color image, so this is using shortwave infrared data to highlight vegetation. Once again, we're looking at San Francisco here and zooming out. And this is the kind of thing that you can do just with a URL, just from anywhere. Like Chris said, this is very much how the web works. Historically, you load HTML documents and you can see stuff. You can load scripts to do interesting things in your browsers. Now you can just load up pixels and render them in really interesting ways as well. So this is QGIS. You can also load cogs in QGIS, and you can use the same exact pattern that was just shown in the slides before, which is you take the URL for the cog, you load it into the application, and it will stream into the application, your desktop application like QGIS, right from the browser. So here's pasting in an HTTP endpoint to a cog, and voila, you can load it up and start looking at it and manipulating it and analyzing it within your application in QGIS. And you can do the same thing in ArcGIS Pro. So I want to take a minute to talk about some of the thinking behind when we launched Landsat on AWS. So it's crazy. This is just about 7 years and 1 month ago that we launched Landsat on AWS. And if you'll indulge me, I'll tell a little story about the origins of this. I had joined AWS in 2014 to build the open data program. And I knew Chris at the time, and he's like, oh, this is cool, you should check out Landsat. I had never heard of Landsat, and so started falling into this rabbit hole, which is awesome. And less than a year later, we committed to host a petabyte of Landsat data on S3. And there were two consequential decisions that went into this that I'll take credit for, and I can explain. And then other decisions that other people made that were foundational to creating a cloud-optimized GeoTIFF. So the first thing was that when we started looking at Landsat, we started talking to a lot of people who use it, and we realized that almost nobody uses all 12 bands of data that come through with a GeoTIFF that you would normally get from USGS at the time. Most people would download the data and then throw most of it away because they only wanted 3 or 4 bands. And so I insisted, let's not host the tar archives. Let's not host the tar balls. Let's make each individual TIFF available. And some people said, oh no, this will break workflows that people already have. You can't really do that. And I said, that doesn't make sense though. We can't host this much data and have most of the data transfer just be wasted. And then the other thing was that I insisted that S3's APIs, the object store's APIs, would be sufficient for our needs. And a lot of people were like, well, no, like people need services. A lot of like what Chris talked about, you need to have a geospatial database. You need to have web interfaces or other application interfaces. People aren't just going to be able to do stuff with the TIFFs. And I said, well, no, because if anybody's going to build one of those services, they're going to need to get the TIFFs at some point. And so let's just make the TIFFs available in a somewhat raw form. And then it was Peter Becker from Esri who was like, hey, you should do this internal tiling thing and add overviews. Really, I mean, the stuff that really makes GeoTIFF sing. I understood none of that. But we trusted him, and we worked with Frank Warmerdam at Planet and Amit Kapadia at Planet to set up the bucket and get the data flowing. And the rest is history. We also added some metadata adjacent to the images so that any Landsat file comes with some metadata. We converted that into JSON using Lambda functions. And that pattern of making data available in this way, that's range requestable, that is programmatically accessible in a bucket that has metadata adjacent to it, has turned out to be a very good pattern. It's worked out really, really well, and it's been really gratifying to see. It was sometime around 2018 when I realized that Landsat stands for land satellite. So just to give you an idea of how naive I've been throughout all of this. But the thinking here was that we did not know what people would do with the data. And that was kind of a good thing because it forced us to put in some constraints and to sort of get out of people's way. And that enabled a lot of innovation that we're going to talk about over the next couple of days. And then these slides here, these are actually slides of a slide from a presentation that Paul Ramsey gave a few months after we launched Landsat on AWS, where I really felt seen by this. It was a great presentation. It's called Data Pipes and Relevance. where he points out, look, the distribution of this data is not user-friendly at all, but it's very computer-friendly. And it allows programmatic access adjacent to computing, which enables a tremendous amount of very fast innovation and experimentation. And the whole point being that if we can make data available to people that was previously infeasible for them to get at scale, will enable a lot more innovation. The other thing that happened, and this is an example of data having gravity, is that a few months after we launched, Evan made, I would say Evan, updated GDAL so that it could read directly from S3. So as Howard said, if you have large volumes of interesting data in an object store, it does create that gravity for people to start building tools around it. And this was a very consequential moment when GDAL could suddenly start reading from S3. And then about 5 years later, as the COG spec hardened, now GDAL supports COG natively as well. And then this is a graph that I've always loved to share that really does show the step change that occurred when we started making this data available like this. So there are about 90,000 points on this graph, each one corresponding to some analysis done by Drew Bollinger at Development Seed. And on the left-hand side, you'll see this cluster of points that of the old way, where you'd have to transfer a tarball every time you wanted to do an analysis, and it takes roughly 375 seconds to do the analysis because you have so much data transfer. As soon as we took most of the data transfer out of the equation by making the data available much more discretely, the time to process goes down to something like 50, 75 seconds, something like that. And we estimate here that this graph shows about 250 days of time saved for the analysis that Drew was carrying out. And this is what a step change looks like. This is the kind of thing that enables much faster experimentation, much higher rate of experimentation for science. And here's the kind of things that this enables. So voila, so here's this ecosystem software. Speaking of being lazy, like how Chris says we want people to be able to be lazy. It is so gratifying to be able to see all this innovation that's happened that we've never had to get involved with, but that's been done on the back of lots of COGs being hosted in the cloud. It's really incredible. You can get a lot of COG data now. It's on the web, and I think as Stack becomes adopted more broadly, it's going to be much easier to find using search engines, things like that. But right now, you can go to the registry of open data on AWS. There's a tag for COGs. The USGS makes all of Landsat Collection 2, both level 1 and level 2 products available as COGs. You'll find NASA products there. You'll find RadarSat, World Bank nighttime light data, various Sentinel products, thanks to Synergize and others. Microsoft's Planetary Computer has a beautiful catalog that includes a lot of COGs, and it's a really cool visualization tool that you can use to browse those and look at them. Planet provides all of its data as COGs. Maxar provides COGs as well. We're going to hear from Airbus later about how they use COGs. And if you go to codegeo.org, there's a data provider section there where you can see more examples. And of course, if anything that's missing on that site, you can make a pull request and add, which is awesome. And there are many, many libraries built on top of this. So again, going back to this notion of primitives and not frameworks, the whole point of making COGs available in the way that we have, or the way that the spec has evolved, is that you really want to make the data available in a foundational, simple way so that people can use whatever tools or whatever framework they want on top of it. And that's what this has enabled. And so we have a wide variety of libraries that people can use depending on the environments that they're used to working in, the language that they prefer to work in. And so I'll give a very, very speedy, because we're over time a little bit, overview of what can be done now with COGs in the web. So this is an example of just using JavaScript and WebGL to work with the data in the browser. So where you're making very precise queries, again, at a tile level, you can actually see the tiles loading up. in the animation here, and manipulating the data and analyzing it within the browser, which is super cool. So you're doing all the compute is happening client side. There are other examples of this. This is from EOX, their Cog Explorer, that will take a URL to a TIFF and render it live in the browser entirely client side, which is astonishing that people can do this. To me, I think it's hard to overstate how significant this kind of thing is, where you're taking software that just about anybody who has a computer with an internet connection has access to a browser, and the fact that you can analyze planetary scale data, raster data, just in the browser without any additional software is mind-blowing. This is what it looks like to democratize access to data, and it's really interesting to think about what people will be able to do with this all over the world. And of course, you can get much more sophisticated. This is what you're seeing here is an animation of Unfolded. I think it's Unfolded Studio, that shows how they can work with cogs and add 3D overlays and really sophisticated visualizations as well. So you can get much more intense. And then finally, Google Earth Engine also allows you to just load up cogs. So if you have a cog loaded up anywhere, you can plug it into Google Earth Engine and take advantage of all of their capabilities, scripting tools, and analysis tools, which is just, again, extremely gratifying. It's really great to see this the spec being used so widely. So this is a lot of flexibility. And then you're going to hear about T. Tyler momentarily, but one thing that I want to point out is that it was a few months after, again, that we launched Landsat on AWS, that AWS Lambda was announced. And this is a common kind of service that you'll find on any cloud platform, which is a very small, very ephemeral, event-driven compute service. So that if you want to run very discrete code on demand, or based on specific events, you can. It's extremely cheap and extremely scalable, and it's being used to create the tiling, engines or tile renderers that are effectively infinitely scalable, that we're going to hear about. And this is just a perfect example of how, when you have data in a public cloud environment, you get to draft off of all of the innovations that the cloud providers are constantly creating. There's healthy competition in the cloud space, so that as new compute capabilities emerge, the data becomes even more useful over time. And Lambda is just one example of how that's done. So I'm going to close there. This has been awesome. It's awesome to see the interest in here, and thanks for attending and listening. Please play with some cogs. Yeah, and you can reach me on Twitter if you want. My DMs are open if you want to talk about anything. Thanks again, Chris, for this opportunity. Thanks for organizing this.
Thanks so much, Chad. That was a really great overview. You want to